This diagram presents a classic analytical geometry challenge. We need the exact size of angle theta, but our starting data is restricted to the circle equation. Solving this requires treating geometric shapes as instructions to translate into actionable algebraic data. Our roadmap follows a specific sequence. We will identify the coordinate points, use them to calculate line gradients, and finally convert those gradients into the required angle. First, we must find the coordinates for center C and the point of tangency at A. The equation is currently in an expanded form that obscures the center of the circle. We begin by grouping the x terms and the y terms together. To reach the standard form, we complete the square. We halve the coefficients of the linear terms, square them, and add those values to both sides. This results in the quantity x plus 3 squared plus y minus 2 squared equals 25. By isolating the values within the brackets and inverting their signs, we find the coordinates for center C, -3, 2. To find point A, we look at its location on the y-axis. Every point on this axis has an x-coordinate of 0. Pause the video here and substitute x equals 0 into the circle equation to solve for the y-intercepts yourself. Solving the quadratic equation gives us two values, 6 and -2. Since the diagram shows point A as the higher intercept, we know the coordinates are 0, 6. Identifying these two sets of coordinates provides the data needed to move from the circle's shape to the properties of its lines. We can now calculate the gradient of the radius connecting points C and A. By dividing the change in y by the change in x, we find the radius has a gradient of 4/3. To reach our final angle, we need the gradient of the tangent line AD, which has a different orientation than the radius. Geometry tells us that a radius is always perpendicular to the tangent at the point of contact. This means the product of their gradients must be -1. We take our radius gradient, find its negative reciprocal, and arrive at a tangent gradient of -3/4. We link this gradient to its angle of inclination, alpha, using trigonometry. The tangent of the angle equals the gradient, allowing us to find the slope relative to the horizontal x-axis. Identifying this gradient is the final translation required to solve for the angles in the diagram. While we have alpha, target angle theta is measured against the y-axis. The axes and tangent form a right-angled triangle. By the exterior angle theorem, theta equals the sum of the opposite interior angles, the 90-degree origin, and angle D, the supplement of alpha. We solved this by translating geometric descriptions into algebraic data. The tangent gave us a perpendicular gradient, the intercept provided a coordinate, and the gradient became a trigonometric ratio.